We'd like to also give a special welcome also to our colleagues from the ITU, Thomas Basilico, Vishnu, and Reinhard Scholl. And just to remind everyone, this challenge was organized as part of ITU's AI for Good Machine Learning in 5G Challenge. So here's the agenda for today. I'll ease us all into the subject with a general introduction and some statistics around the competition. Then we progress rapidly to the much anticipated award ceremony with Ivo Bolsen, so the Xilinx CTO. And then we'll get 4 lightning talks from the top submissions that we had. And in the last 30 minutes, Yaman and Felix, can you please get on mute? I still hear a lot of noise on the line. So, and in the last 30 minutes, Yaman and Felix will tell you a bit what can happen when you put your DNN onto an FPGA. Can you please go on mute? I still get the noise on the line. Okay, so let's remind ourselves what the task at hand was and what we're trying to achieve. So the application we're considering here is modulation classification for RF signals. Essentially, we're looking at the raw RF samples coming from a radio front end and trying to find out which modulation is being used. This is a way of rapidly labeling and understanding the RF spectrum, which is a key enabler for many applications, such as monitoring the spectrum for interference, detecting radio faults, dynamic spectrum access techniques, as well as numerous regulatory and defense applications. Although it's possible to use classical machine learning techniques to approach this problem, prior work really suggests that deep neural networks are a great match for this problem, especially for short-time observations. A key challenge for RF modulation is inference throughput, though. Let's view the modulation classification in a radio deployment as a pipeline to illustrate this. So we have our RF signal coming in on the left-hand side of the slide, which will first be sampled and converted into a digital domain, and then go through quadrature mixing and decimation to obtain a stream of samples. This stream of samples will have a high data rate, possibly in the order of gigasamples per second. And these will feed eventually into our neural network for classification. And that's exactly where the challenge comes from. So if you want to keep this pipeline running at sample rate without dropping anything, we have a very high inference rate requirement. And by the way, there's a similar story around latency if the classification output is part of some form of control loop, although we're not discussing it here in further detail. So in summary, the goal behind this challenge is to break speed records, to put it simply. So to enable many future DNN-based RF applications with extreme throughput and ultra-low latency. To achieve this, the teams had the following job. So first of all, train a DNN to do modulation classification on the RadioML 2018 dataset from DeepSeq that achieves at least 56% average accuracy over all SNRs, while minimizing the inference cost. And to support this, our team here at Xilinx provided you with a sandbox environment where you can train highly specialized DNNs with quantization-aware training, a training script for a baseline DNN model to get you started, and of course, general support, evaluation, ranking of the submissions for the global round on the basis of the inference cost. This is what the timeline looked like. Competition started back in June. Submissions were due beginning of October. Since then, we reproduced all the results and carried out the evaluation. Today is the day where we will announce the winners and have an award ceremony, in fact, in about 2 minutes. And most importantly, the top 3 then progress to the final round. So let's take a quick look at the submissions and the statistics now. As you can see, we got submissions from all over the world for a total of 41 teams registered with 66 individuals, out of which 13 teams with a total of 32 participants submitted with at least 1 entry. So which is truly fantastic. Thanks so much for all of your contributions. And as we hoped for, we had lots of interesting approaches. Here we try to summarize the techniques taken. Most teams adopted variations of the baseline topology with a mixture of quantization and pruning, Some teams switched to more efficient mobile net-like topologies, and some individuals tried decomposition and feature engineering. The winning team here uses a magic mixture of the above techniques. And here's a plot of the result scores of all 13 contributions, each represented by a red bar. Hold on with extrapolating your own position yet. It's going to be revealed shortly. So the y-axis is inference cost on a log scale. Our baseline, as handed out in the sandbox, is at inference cost 1, and the higher the bar, the better is the submission. The winning score is on the far right, and you can see it's a clear winning contribution. However, there was a really close competition for the second and the third place. Also worth mentioning, the submissions achieved an over 60x improvement compared to the baseline, which is truly magnificent. And now let me pass you on to our CTO, Ivo Bolsens, for the results.
Okay, well, good morning, everyone. And first of all, I would like to extend my thank you to the ITU for being the catalyst of this initiative. And I would also like to thank everyone who has participated. In the end, we have identified 13 cases that went above the baseline in terms of the figure of merit. And of course, congratulations to all of them who managed to achieve that. But of course, as in every competitions, there are some winners that have to be recognized and awarded. I think this competition is really representing some of the things that are going to become very important in the future for our world, right? There are today a lot of big technologies that are being developed, and previously a lot of developments happened in these jointed fields, such as artificial intelligence and mobile communications. This is a good example of how two worlds of emerging technologies are building on and amplifying one another. And clearly, some of the outcomes of this combination of technologies will alter our business and our social landscape and might have truly the potential of disrupting, the status quo in how the way people work and how people live. So I think this competition is a good example in how we combine two technology fields that have the potential in really transforming the global economy for the next 5 years. So I think I cannot state enough how important it is to get this cross-field kind of interactions. And once again, congratulations to the winners. So with that, no further ado, let's see who made it to the third place. So, the third place winner is the project called, or the team called Aronica, and they reached an inference cost score of 0.046007, which is 22 times better than the starting point that we gave everyone. So congratulations for that achievement. And the team members of the Aronica team are Mohammad Chegini, Poya Shiri. Congratulations. And then second place, very close, is the AMC team, which got an inference cost score of 0.042467. Only an engineering competition, you cannot get these kind of scores, I guess. And they achieved 24 times better than the baseline. The team members of the AMC team that we would like to recognize are Jacob Riston, Rajib Patacharya, and Andrew Stark. Congratulations to the AMC team. And then finally, the first place and the winner is the team called Bacalonet. And the cost score they achieved was 0.016211, which is an astounding 62 times better than the baseline that we gave everyone. And the team members are C. Rosa, Guilherme Carvalho, Daniel Granau, Iago Gonçalves. Congratulations, to the team. And with that, we will hear now a little bit more about some of the projects. And I hand it over to you, Michaela, to introduce the projects.
Okay, so just from my side, quickly, I want to show for all the other participants on where they ended up in the ranking. So take a moment to digest the numbers. It's a bit of an eyesore. We also published the results under the link up here, which Yaman no doubt can put it in the chat for everyone to access. So you can also look at it offline and dissect the results in peace and quiet. So we're going to hear now from the three winners and also from the Imperial IPC submission, because we thought it was of great interest to everyone else. Alessandro, are you online? Can you do the introduction?
Yes, so thank you, Michaela. As we mentioned, so the submission from Imperial was not among the winners, but was definitely among the most interesting in terms of the choice they made from a topology point of view. So we decided to give them some space to present a few slides on their work. So if the person presenting for Imperial could share their screen with the presentation, you have the stage.
Yeah, sure thing. Just allow me a second, please. Yep, this. And yeah, are you able to see the screen right now and the presentation? Yes?
Yes.
That's great. So again, hello, everyone. My name is Mikołaj Jankowski, and I'm a member of the Imperial IPC team, which is a part of Imperial College London's Information Processing and Communications Lab, supervised by Professor Denis Gunduz. So it's a great honor for us to be invited to present at this workshop. And today I will walk you through our solution to this modulation classification challenge. I would like to start by showing you the overall architecture and data processing flow for our algorithm. And as you can see from the figure, we introduce multiple modifications to the baseline neural network. So first of all, instead of merely considering a convolutional neural network as a feature extractor, we introduce two preliminary processing branches, one of which extracts convolutional features from the raw data samples, while the other one processes meaningful handcrafted statistical features of the input signal. Outputs from both branches are then concatenated into a single vector and processed by a fully connected classifier head to produce the final predictions. In order to optimize gradient flow within each of the branches, we introduce two auxiliary classifiers, each of which considers only the output from one of the branches. The auxiliary classifiers are only used during the training phase and are removed during the evaluation. This network structure allows us to improve upon the baseline accuracy by 2%, which gave us a better starting point for our pruning scheme that I will discuss in the next slides. Let me now share with you the architectural details of our network. The convolutional branch preserves structures similar to the baseline with a few slight changes. Firstly, an average pooling block was added to the beginning of the network. So when we were running our pre-analysis, we found that this pooled input size managed to result in sufficient classification accuracy while significantly reducing the computational burden. Another hypothesized benefit of such preprocessing is that it effectively denoises the data by averaging over the pairs of time samples. The second change that we introduced to the convolutional network was changing the stride for each convolutional layer to 2 and removing the max pooling operations. So while maintaining the output size at each layer, this reduced the number of operations required by each convolutional layer by a factor of 2 with none or minimal loss in the final accuracy. Our linear classifiers are very similar in structure, and they consist of linear layer with batch norm and ReLU and a single linear layer with softmax activation that maps intermediate features into a length 24 probability vector representing class predictions. In the bottom right corner, you can see a list of handcrafted signal features that we use as an input to the second branch of the network. These include central moments of the real and imaginary part of the signal, instantaneous properties of the signal based on the Hilbert transform of the raw samples, and the higher order cumulants. Use of these features was partly inspired by classical modulation classification methods, including the paper described below, written by Amin Abdelmutallab and others. And finally, I will talk about our training and pruning pipeline along with the results. In the first phase of the training, we simply pre-train the network with the sum of cross-entropy losses for each of the classifiers. This part of the training is run for 20 epochs. Following on from this, we perform repetitive pruning and fine-tuning steps. At each pruning step, we remove 15% of the weights remaining in a network with the lowest absolute value. We then run a fine-tuning training step for 20 epochs to regain the accuracy. The loss function we utilize during the fine-tuning is a sum of the previously used cross-entropy loss and the knowledge distillation loss inspired by the paper Distilling the Knowledge in a Neural Network by Geoffrey Hinton and others. In this part of the loss, we simply replace the ground truth labels with the predictions of the unpruned original model, which acts as a teacher, whereas the pruned model is considered a student. This is inspired by the idea that the students should not necessarily make correct predictions, but simply ones that are similar to the teacher model. So we repeat the pruning and fine-tuning procedure until we encounter a significant drop in the performance. In one final step, we manually reduce the bit width of the network for a number of different layers. In our submission, we were able to reduce the bit width of all the layers from initial 6 to 5 and even to 4 bits in some of the layers, which brought significant improvement in terms of both computational and memory efficiency. As you can see in the table on the right side of the slide, our best performing network achieved a score of approximately 0.11 while staying above the required accuracy threshold of 56%. So that's it. Thank you so much for listening to our solution, and hopefully the steps are clear. But if you have any questions, we'll be happy to answer them now. Thank you.
Thank you, Mikolai, and definitely a very interesting approach. I can see how using these manually extracted features can help improve on efficiency. So are there any questions for him or the rest of the team from anyone in the audience? Please let me know. Feel free to unmute yourself or write in the chat. Otherwise, I guess we can go on with the next presentation, and we're gonna hear now from the third ranked team, so the Aronica team. You're invited to take control of this stage and share your screen and your presentation. Aronica team, are you there with us? I guess maybe they didn't join.
Are Mohammed or Puya present in the call? Oh, okay. They're having technical problems in the chat.
Okay, maybe we want to go to the next one first and then come back.
Yeah, let's do that. So let's move for a second to the second ranked team. So the AMC team, if you want to take the stage and share your screen, you're welcome to present.
Hey everyone, you can see this, right?
Yes, thanks.
All right. Well, yeah, as the previous group mentioned, we'd really like to thank ITU and Xilinx for hosting this competition. We had a lot of fun with it. So I am Jacob Kristen. I'm speaking on behalf of the AMC team. We're out of Georgia Tech Research Institute. And so I was accompanied by Rajiv Bhattacharya and Andrew Stark as well. So this whole competition is on the premise of balancing two variables, kind of speed and accuracy, kind of accounting for different trade-offs. So we wanted to explore a few knobs you could turn regarding each. So one notable knob you can turn regarding to speed of your network is changing the architecture that was provided. However, we did not change the architecture. We wanted to focus on pruning and quantizing, as that was really what was novel for us on our end. So we had a lot of fun with that. So regarding the quantization, we were able to reduce the VGG style provided network down to 4 bits from 8 bits, and it was 4 bits for both the weights and the activations. We did go ahead and prune the weights. We used iterative magnitude pruning, which is essentially you train the network, you prune it a certain amount, you prune it based on the magnitude of the weights, you retrain, prune it again, so on and so forth. However, in our case, typically when you do iterative magnitude pruning, you will prune until completion. However you define that, we defined that as when we would reach the accuracy threshold in our validation law, or in our validation, and we used an L1 unstructured pruning method in our iterative magnitude pruning. Additionally, so as I said before, that speed accuracy trade-off, something we tried to use to encourage greater accuracy was a learning rate scheduler, and we used what's called reduce LR on plateau. Essentially, it's a paradigm where if your validation loss is stagnant, it will reduce your learning rate because it assumes you're in a convex bowl and you're jumping across side to side. So if you reduce your learning rate, you can find that local minima, squeeze out a little bit more performance gain. So here is our overall architecture. Again, it is exactly what was provided to us. We wanted to focus more on the quantization and compression. Here's some pseudocode for iterative magnitude pruning. So again, for every pruning step, you train it. Then once you hit that accuracy, which for this competition, 56%, you'll save the model, you prune it. In our case, we pruned it 20%, and then you'll go ahead and then retrain that pruned graph. We got this 20% from a tweet. So Alex Renda is a researcher at MIT who's done work on pruning, and this tweet is regarding his work on learning rate rewinding. Sorry about that. And so here's kind of a 4-step tweet on how he does it. But essentially in this tweet, he says a heuristic for iterative magnitude pruning is 20% every time you prune. So that's exactly where we got this 20% from. Over here on the right, we summarize how well our compression and pruning methods did. So we were able to reduce the bit operations in the weight bits by 2 orders of magnitude. The overall compression ratio that we were able to get purely from pruning alone was 9.3, which yields a sparsity of around 89%. And so just some quick notes. In hindsight, we actually did not implement the learning rate scheduler correctly. So there may have been some performance left out on the table. So that's something that we hope to revisit. And here's just quickly how we computed the sparsity percent compression ratio. We had 10 iterations of pruning, and we kept 80% of the weights every time. So that's how we were able to get these numbers, in case anyone was curious. And finally, here are our results. So our normalized inference cost was 0.04 while achieving the at least 56% accuracy. And here are the corresponding plots to help you better understand where the strengths and weaknesses of our final model are. Thank you very much. And if you have any questions, I'm happy to answer.
Thank you, Jacob. And again, if anyone has any questions, feel free to write them up in the chat or just unmute yourself. Otherwise, yes, please go.
So I have a question. I'm Kees Vissers, work at Xilinx. So in the end, you reduce every time 20%, but you leave still a very small fraction of accuracy that you could have reduced on the table, right? If 5600 was the goal and you're ending up at 5625, I can imagine that another step of 20% will get you below that accuracy. Would pruning of the last percentages still help here?
I'm sorry, can you repeat that last sentence?
Would pruning in the range of not 20%, but just 1% or 2% sort of infinitesimally approach your 5-6%?
Yeah, I'm sure there is. Again, we were following that heuristic. That is a fixed rate pruning method. So yes, I definitely agree. You know, if we were to, go 20, 20, 20, et cetera, and then once we, maybe had some feedback in there where if we pruned it and we couldn't get back up to 56%, then try it again, but prune it 10%, maybe half it until, yeah. So, I mean,
Right.
I'm sure that there's still a little bit more room there on the pruning. Yeah, I agree.
Okay, thank you.
Thank you. And then I see a question in the chat asking what was the runtime for each iteration. So I guess the training runtime with your setup for each of those 10 iterations. How long did it take? Maybe in terms of epochs?
So I want to say, so we used I have access to a Quadro RTX 400. So just so people have that baseline in their mind. So that's what I used to train. And I believe it was on the order of 7 minutes.
Okay, yeah, that's pretty quick.
I recall. Yeah. Yes. So I guess just speaking to the runtime here. So typically when you use iterative magnitude pruning, you reset the weights every time you prune because iterative magnitude pruning is state of the art for what's called the lottery ticket hypothesis. Anyways, we did not reset the weights. So that did speed up the actual runtime of this entire paradigm because we started with a pre-trained prune graph every time so that it really cut down the amount of time needed to run entire scripts. And I think 7 minutes is a bit of a, maybe in the beginning it was 7 minutes when there was more learning, but then, the time between pruning was not consistent. Sometimes it was 1 or 2 epochs, then it would prune. Sometimes it was 1, sometimes it was 5. So, I mean, it's all on average.
Thank you. Yeah, that makes sense. So unless there are any other questions, maybe we could try to go back to the previous presentation if the technical issues have been solved. Mohammed?
Can you hear me?
Yes, we can hear you.
Hi, very good. And I believe my webcam is working all right. Yes. And so let me share my screen. Okay, this is our submission. This is a presentation of our submission to this challenge, and the team members are I myself and Puya. I am affiliated to Shahid Beheshti University in Iran, and Puya is a PhD student in University of Victoria right now. First of all, what are the possible solutions? And I don't know what is wrong with the timer. The possible solutions are there could be a lot of solutions. One might have, I don't know, just momentarily, I don't know what there's wrong.
Feel free.
Is this something that happens on Zoom? Because previously it was working all right and there was no timer in the slideshow.
It might be that the timer got enabled, but if it's simpler for you, just feel free to share your screen without necessarily going into presentation mode. There might be something to untick in PowerPoint to disable the timer. But
okay, just a second. I believe this will be all right now. I'm sorry for the problem. We don't normally use Zoom here. So,
no worries.
That is where the problem might arise. Anyway, I think it's all right now. So the possible solutions, there are a lot of possible solutions. There are a wide family of neural networks trained on the ImageNet. And here are some candidates. For example, you see the VG that was provided to us by the organizers, that you see they are somehow beefy neural networks. They aren't very efficient. However, you can see that, for example, the top left is the best one, obviously. For example, you can see the ResNet family, and I believe some participants use that. Or, for example, the MobileNet V1 or MobileNet V2 or NASNet or other stuff. And obviously, those would be the aim of any participant, in my opinion, to go through. That could be correct, but not quite, because, for example, you see that in MobileNet V2, we have an inverted residual block, and that inverted residual block has got an expansion ratio, and that expansion ratio could be a lot, which is something that we do not necessarily need. Or, for example, in ResNext, although it does divide the input channel into multiple paths. If you add this SE block, this squeeze excitation block, that will be problematic, because you're adding linear classifiers, and we should be avoiding any kind of module or self-attention mechanism, namely the SE, and that is trying to increase the inference cost. So just let's take a step back and look at the inference costs that were kind of possible in my case. For example, here we have the VG10, which has a precision of 8 bits and 64 filters. In this family, all of them have the same. And as you can see, even with the expansion ratio of 3, the MobileNet V2 is pretty much useless. Or in the third case, you can see that even the MobileNet V2 is performing worse than the other two candidates. But as you can see, for example, the first and the third one, you can see that the MobileNet in the first version, generally the idea of pointwise convolutions, they are better, and we could have a compression ratio of 2, almost 2, 1.7, 1.8. And this was my final submission, 0.046, which I used a MobileNet and iteratively pruned that MobileNet just one time. I wanted to raise a point, and that was I trained a network for 24 epochs, and then I trained it, I fine-tuned it for another 3 epochs, which took me about 54 hours on a P100 is a very good GPU, right? It took that long, and I saw other teams, obviously one of the criteria for the submissions was that we needed to publicize our code on GitHub. And you can see that a lot of teams, like I saw one which trained for 200 epochs. I saw ones that were higher than that. So I think that is a very good food for thought, that one might actually consider that, because the inference cost, that is absolutely crucial. However, the training is also crucial. And the next, I wanted to talk about the pruning. This was the result of that 24 epochs that I had. This is the weight distribution for the main network, which had a similar accuracy, 56.3. Obviously, the capacity is, I believe, that is higher than the accuracy that I achieved, but I wasn't able to train any further. Here, after just pruning, I pruned, I believe it was 15% of the weights, and then trained for another 3 epochs, and I lost next to nothing during this pruning. And as you can see, after I pruned during this fine tuning, I burned in the weights. Obviously, you cannot, we are doing unstructured pruning, which you cannot really, delete from the graph of the PyTorch or other frameworks. But you could, do not let the errors backpropagate, and thus, just kind of eliminate those neurons. So that was the result, and I achieved an accuracy of 56.1 and an inference cost of 0.46. So yeah, that was my presentation. And yeah, there's a compression of 21.7, almost 22 times. Thank you for listening, and I'm happy to take any questions, if any.
Thank you, Mohammed. And again, if there are any questions, please feel free to speak up or write in the chat. I also see there is a general question from Vino, but I think we can take that later on. No questions, then I guess we can move on with the final presentation from our winning team. And the team is free to take the stage.
Yeah, sure. So can you see?
Yes.
Okay. So hi, everyone. First of all, I would like to thank Xilinx and ITU for having us in this competition and everybody present. So we are the Bacalhau Net team. It's composed by José Rosa from Polytechnic Leiria and Daniel Gagnan, Tiago Gonçalves, and myself, Guilherme Carvalho, from University of Porto and UNESCO. So to tackle the problem at hand, we developed an architecture featuring depthwise convolution and residual connections. Design space exploration was used to both optimize inference cost and accuracy. So in the end, the final architecture features 5 layers in total, with decreasing one-dimensional kernel sizes according to depth. It also has variable stride length and number of output channels according to each layer. So the first 2 layers have 24 channels each, and the final 3 convolutional layers have 48 channels. To improve the inference cost, we tried both quantization and pruning, as most of the other teams have. So quantization, we tried multiple bit widths for both inputs, weights, and activation. No significant accuracy loss was reported up to or down to 6 bits. However, below 6 bits, accuracy degraded significantly, and it proved even impossible to reach an accuracy above 56%. Therefore, a uniform width of 6 bits revealed to be the best compromise between inference and accuracy. After performing quantization, we also tried structured and unstructured pruning. So pruning of entire channels revealed to have poor performance, and we discarded it completely. And then we passed on to unstructured pruning. So here we had a lot better results, and it provided the best cost reduction with iterative magnitude pruning. So between each pruning step, training was performed with an associated weight decay to induce sparsity. And values below a certain threshold. In this case, you can see in the table the minimum weight absolute value were reduced to 0. And after that, the network is then retrained. So as it can be seen in the table, we managed to get a reduction of up to 88% in the inference cost with only 3 pruning iterations. And that's it. Thank you so much for having us. Any questions, feel free.
Thank you for your presentation. Again, I'm going to leave some space for questions.
I have a small question. So you mentioned that you did the design space exploration to find the topology and then later on to find the pruning parameters. Can you tell us maybe how many different kinds of topologies did you try, or for how long did you try that, on what kind of hardware, just so that we can have a rough idea?
Yeah, so how many? Well, we did try a lot. We had at our disposal, we had available, I think it's 5, 5 GTX 1080, I think. Yeah, I think that's it. And we probably tried, I don't know. We did try a lot.
Maybe hundreds.
Yeah.
Okay, so you probably had automated scripts for all of that. And
Yeah.
I saw in your submission you had like, okay, you had spreadsheets and everything was automatically passed and it looked very explorative, yeah.
Yeah, exactly.
Okay, thanks.
Thank you, Tim, and thanks everyone for sharing your work.
I had a question.
Please do.
From the top team, how many epochs did you train for?
How many, sorry?
How many epochs did you train for on your final network? I mean, after doing the neural architecture search.
Well, so because it's with the pruning involved, we have to do 3 trainings with no, 4, sorry. Yeah, the first training, yeah, so 4 trainings with regularization, each training 20 epochs. So in
Great,
total,
thanks.
it amounts to 100 epochs, I would say.
Great, thanks.
So.
Any more questions for our winners? All right then. So I see, just to go back to a question that was asked in the chat, Vinod was asking if there is a trade-off with respect to signal bandwidth and SNR of this signal to be classified. That's an interesting point. I personally, I would say probably not, in a sense it depends on the particular signal. Felix, do you have any comments on this based on your experience?
Yeah, not really, because based on the data set we are using, we have only these baseband signals. So we don't really have any information from what kind of bandwidth these have been sampled. And I believe due to this circumstance, it's not really a factor for us here. Maybe Yaman can add something, but.
Great. I'll just remind everyone to please mute themselves if they're actually asking a question or for the whole audience. No, I wouldn't have too much more to add there. I don't know if there is actually anyone from DeepSig in the call. They might actually be able to say something about that. The only comment I could possibly make is we did see a significant effect across all SNRs if we sort of further subsampled the signals, instead of using the whole 1024 samples, we sort of pulled that in some way or the other. We did usually see some detriment, but that's yeah, probably not too surprising. That's the only thing I can add.
Thank you, Yaman. So we can move on with our workshop, and we're now at the stage where we're gonna give a short presentation about how things could actually move forward from training a model to getting it running onto hardware, in our case with our Fin toolchain. So Yaman and Felix, feel free to take control of the stage.
Thank you, Alessandro. And once again, congratulations to, well, really all of the participants, but especially the top teams. I hope you can see my screen.
Yes, it's all good.
Great. Then I'll also bring up the laser pointer and off we go. So in this challenge, right, you've trained these specialized DNNs, right? You've applied these specialized techniques for quantization, sparsity, topology design, custom training techniques, which we're very happy to see, all of which were utilized across the board to actually obtain these accurate DNNs with low inference costs. So where do we go from here, right? Is that actually enough? How do you actually deploy such a specialized DNN as part of an application that needs fast and accurate RF modulation classification? So as we alluded to before, that's going to require some specialization of the underlying hardware architecture as well that implements this DNN. And that needs to sort of provide some capability in terms of interconnects, arithmetic flexibility, being able to tightly integrate radio and compute, and some large internal bandwidth to do all of this with enough throughput and latency. a quick refresher on FPGAs and Xilinx RF SOCs, for those who are not familiar. FPGAs are this kind of reconfigurable hardware platform, which is primarily primarily consisting of this sea of programmable dots or lookup tables, which can be in the number of millions, right? These can implement any logic function when they're connected together by this programmable interconnect. Modern Xilinx FPGAs, they also include these digital signal processing slides for actually doing operations like multiply accumulates, and there's a lot of embedded SRAM or block RAM, ultra RAM distributed around the chip for high bandwidth. On top of this, Xilinx, we have these fantastic devices that are called RF SOC, which further enhance the heterogeneous composition of this chip with ARM processors, as well as an integrated RF subsystem to actually directly create these software-defined radio front ends, which we think is a pretty good match for this hardware architecture specialization side of things. So then, how do you bridge this gap? How do you make your specialized DNN take advantage of the FPGA fabric? This is essentially the aim of the Fin project, to provide a fully open source, customizable end-to-end solution stack for highly specialized DNNs on FPGAs. Typical flow in this solution stack looks something like this. You first train your specialized DNN with various algorithmic optimizations. By now, I think we don't need to say too much more about this, because this is essentially what the competition was about. So for this, you can use Brevitas. I'm happy to briefly mention here that in addition to Brevitas, we'll soon be supporting TensorFlow-based QKeras as well for actually developing these networks. This trained network will then get exported to an ONNX intermediate representation, which you are also subjected to as part of the submission requirements. And that representation is going to go into the Fin compiler, which I want to say a few more words about in a moment. The compiler at the 30,000 feet level is going to generate a specialized dedicated FPGA accelerator for this DNN. And this generated accelerator can then be integrated into a system and deployed on various Xilinx platforms, including Alveos and RF SoC devices. In the kickoff webinar for the competition, we mentioned that FPGAs were a great match for specialized DNN inference, that they could take advantage of arbitrary bit width quantization to implement low-cost MAC operations. You could use different quantization on different layers. You could have fine-grained sparsity, and you could have layer parallel data flow implementations. A lot of the teams in the competitions have actually used these techniques to lower the inference costs, and you'll be pleased to hear that Fin is actually able to take advantage of most of them, including the arbitrary bit width, mixed quantization between layers, the layer parallel data flow implementation. When it comes to sparsity, structured sparsity techniques like channel pruning are fully supported and will be exploited by the compiler, although unstructured sparsity is only exploitable with what we call full unfolding. More on that in a second. But what does this DNN to hardware flow look like in practice? There's nothing quite like actually getting your hands dirty with this, and that's what we would really like you to do. But here's a quick overview of the Fin compiler flow to give an idea. So here we have our input model, right, exported from Brevitas in a specific flavor of the ONNX format with additional quantization information. It's essentially a graph of layers, right? We have convolutional layers, batch normalization, etc. So this graph, this ONNX graph, goes into Fin's automatic build tool, which you can control from command line or via scripts. And it's going to perform a series of transformations to map these individual layers to what we call high-level synthesis building blocks of our library, which are then going to be stitched together in a Vivaldo block design, including pink data movers and drivers, if you so desire. The whole thing is completely transparent, open source. You can interrupt this flow, you can add your own steps, and you can also do verification and simulation using various levels of abstraction, including Python, C++ simulation, or Verilog RTL hardware simulation. One thing I would like to point out for perhaps our participants who are not too familiar with hardware is that this resulting representation is essentially each layer getting its own parallel hardware. They're all operating in parallel, and they're talking to each other. They're sending the activations that they're producing to the next parallel layer with on-chip streaming data flow FIFO links. A brief word about performance. There are two ways to instruct this flow on how it should be implementing the accelerator. It is quite flexible. One thing you can do is to actually provide a performance target and a target device so that the parallelization, how much resources is allocated to each of these is determined automatically. That's quite handy for starting out with a quick turnaround time. Additionally, if you're a power user, or if you'd like to further refine the results, what you can do is actually use that as a starting point, and you can provide a manual configuration per layer that decides how much parallelization, what kind of resources on the FPGA to use, etc., for fine-tuning. And before I pass you on to Felix for all the really good numbers, a quick word about performance scaling and resource scaling. So one of the differentiators we have in streaming data flow architectures on FPGAs is the ability to scale to meet performance and resource requirements. This is controlled by two key parameters, the clock frequency and what we call the folding factor, which controls the degree of parallelism and time multiplexing inside each layer. Clock frequency is proportional to performance. Folding factor is essentially inversely proportional. So making this slightly more concrete, like let's say we have some design. It has a 300 megahertz clock and the folding factor of 10. This can run inference every 10 clock cycles, or yield an inference result every 10 clock cycles, which translates into a performance of 30 million inferences per second. It's 300 million divided by 10. That's going to come at a certain FPGA resource costs, here illustrated with the red boxes and the blue boxes for different kinds of FPGA resources. If our system has a tight resource budget, we can scale this down by increasing the folding factor, let's say by a factor of 100 to 1000. This is going to result in a slower design, which is going to give us a performance of 300,000 inferences per second, but it also fits in a much smaller resource footprint. Conversely, if we're not resource bound and want maximum throughput, we can turn the folding factor all the way down to 1, which will yield a design that uses more resources, potentially quite a bit of resources, that can now do inference at clock frequency, 300 million inferences per second. Unfortunately, in our case, even the smallest RadioML DNNs that we have observed or have seen as part of the competition are too big for this kind of unfolding. So the prototypes you'll be seeing later from Felix are closer to the right-hand side over here. And with that, without further ado, let's talk about what Finn can do for RadioML. Felix, would you like to take over the screen share control?
Yeah, sure. Give me a second. Can you see this?
Yes.
Okay, so I'm Felix, and I'm going to share with you some of our first prototypes. So we based all of our prototypes on the same baseline topology that you all know by now, the same one-dimensional CNN called VGT10. And we chose this model because its performance has been proven before and because of the simple structure, which allows us to get a faster turnaround time in Fin because we don't need any extensive manual design effort to bring this into the compiler. So just to recap, we have a concatenation of 7 convolution plus max pooling layers, followed by 3 dense or fully connected layers. And the input shape is the whole 2 by 1024. And we treat the complex samples as 2 separate channels for the in-phase and the quadrature component. So we also still use the normal convolution operations and no special complex variants. Then we do quantization aware training using gravitas, of course. And since the data set is in floating point format, the first question is always the input quantization. And in initial experiments, we found that 8-bit precision is a sweet spot. And so we chose to keep the inputs at 8-bit and do that with a predetermined scaling and clipping range that we determine by doing statistical analysis of all the highest SNR data points. And the quantization range that we chose then was about 98% of all the highest SNR data points. So we don't have a lot of clipping. And this is also the range that we provided inside the baseline or in the sandbox for you.
I think the slides are not advancing. Could that be?
No, that should be fine.
It's the same for me, Felix. I still see the section separator slide.
Oh, really?
Maybe Yaman, you can manually forward it.
So Felix has taken over the screen sharing. But,
my screen.
Okay. I suggest you either stop and restart the screen sharing, Felix. Otherwise, I can present and you can take the keyboard control.
There's a cloud symbol with a red blinking dot in it. A second. Better?
Yes. Can you try advancing to the next slide and come back to the previous?
Yeah.
Okay, now it seems to work.
Weird. Yeah, so, but you didn't miss much here. So it's just the baseline topology. Yeah, we use 8-bit inputs throughout. So while we vary the weight and activation precision on the next slides, keep in mind that the input is still always 8-bit. And also similar to the provided sandbox, we train on the whole data set regardless of the SNR. And if we were only after the accuracy at high SNR, we could probably get 1 or 2% more accuracy across the bank by leaving out some of the low SNR training samples. And that is at least according to our own experiments. And there were actually some of your submissions, most notably, that also left out samples below a certain SNR threshold. But they did so without sacrificing the overall accuracy because we had the overall goal of 56%, right? So I think they did an amazing job on maximizing the peak accuracy on top of reaching this overall accuracy requirement. And that means that we should probably also look into more clever SNR cutoff threshold in the future. And also note for our results that we did not aim for any specific accuracy minimum. We just tried to find a general trade-off between accuracy and cost. So this slide gives an overview of the most interesting training results. The top graph here shows both the overall accuracy in light blue and the high SNR accuracy at 30 decibels in dark blue. And the bottom part shows the analytical inference cost in million bit ops. So first we started with a floating point baseline, which, by the way, is significantly better than some other floating point baseline for this VGT10 that we have seen. And this reaches about 61% overall and 95% ISNR accuracy here. So naturally, the bit ops metric for floating point operands for this network explodes, and it's literally off the charts here. Next up, we then trained variants with homogeneous quantization, so all weights, output activations, and either 8, 4, 3, or 2 bits. And as expected, the overall and the high SNR accuracy suffer by roughly the same margin, while the inference cost decreases quadratically here. And the accuracy drop is especially deep when we go below the 3-bit mark, as you can see. But luckily, we could recoup some of this accuracy by handling the first convolutional layer differently. It seems to be more sensitive to harsh quantization, so we increased precision to 4-bit only in the first layer and keeping the rest at 2 bits. And the inference cost impact of this is minimal, but we could recoup well over 2% overall and 5% high SNR accuracy. Then we have an additional configuration here, which shows how we can increase precision of weight and activations separately. And the latter are less sensitive in our experience, so that we can combine 4-bit weights with 3-bit activations for a model that sits between the homogeneous 4-bit and 3-bit networks in terms of accuracy and inference cost. And by that, you can already tell that we could fine-tune a lot on this space to find a Pareto-optimal solution for the requirements of any given system. And that is only by adjusting the precision and not even the topology. So without diving into the huge task that would be neural architecture search, we also experimented with smaller and larger versions of the model. And remember that by default, we have 64 channels or filters in the convolution layers and 128 channels in the dense layers. And here we doubled the channels for the convolution layers for the 4-bit model. And we see that the accuracy is almost the same as the 8-bit baseline, but so is the number of bit ops here. So this makes it not really worth it. And then we even continued by increasing the number of channels in the dense layers as well. And here we begin to see the accuracy dropping actually, which is likely due to overfitting. Now on the other end of the spectrum, we also halved the number of channels in the convolutional layers. And this brings us into this very cost-effective territory here of around 60 million bit ops. And compared to the results over here, it seems like this smaller model with 4-bit seems to be more viable than a larger 2-bit model. So based on that, our main takeaways are that we only have a minor accuracy deficit if we stay at or above 4 bits, and that our peak accuracy for the highest in our case even beats our floating point baselines if you compare it that way. And then we selected, based on this, these 3 models here for further prototyping with Fin. And this table gives an overview of the resulting prototypes running on a RF stock board, the ZU111 at 200 megahertz. Implementation A is the mixed 4-bit and 3-bit model with the highest accuracy and cost, and B is the low precision variant of that, and C is then the smaller 4-bit network. So we run these at 200 megahertz, and we managed to take in the samples at clock rate. So minus some pipeline inefficiencies, we reach 190 million samples per second and latency of 60 microseconds. So keep in mind that one frame that we process in our network consists of 1024 samples. So this is why we use here the samples per second metric instead of frames per second, but it's equivalent if you will. And also what you will notice right away is that all of the 3 prototypes have the same performance. And that's actually because of the reason that Yaman mentioned already. They are not bottlenecked by the device resource constraints right now, as you can also see by the utilization numbers here. Instead, they are bottlenecked by a thin tool flow limitation that prevents us from processing multiple samples in parallel. And this limits the amount of unfolding that we can apply to the accelerator. So you only see the resource footprint decrease here, but you don't see the throughput increase. And we are currently working on this bottleneck to further scale up the performance, of course. So the most accurate model here with 91%, even the largest one, tops out at 200K lookup tables, but only 360 loground blocks. And this also indicates that for models of this type, the memory for the weights is unlikely to become a limiting factor anytime soon, especially when you consider that this device has additional ultra-RAM resources, which we don't even tap into here. So of course, it will be interesting for you to see how our prototypes fare against your submissions. And here you can see the top 3 submissions against these 3 prototypes from the previous slide. And we also put here what makes up the inference cost. So the bits used for weight storage, the bit ops, and we also check the sparsity. So the amount of 0 weights and 0 multiplications. And also note that the W bits here and the bit ops are already considering the sparsity in them. And also that our sparsity is quite low because we did not apply any kind of explicit pruning. So just by looking at the cost score here, you see how efficient your solutions are compared to our prototype. And especially compared to prototype C, because that is a fair comparison since it reaches also about 56% overall accuracy. Thanks. Okay, so we can also now see our real-world resource utilization results from the previous slide next to that. And now things get a little bit more complicated. So we see that the cost score is a useful guide for these prototypes, as you see that the lookup table usage roughly decreases with the cost score. But we also see that it's not a perfect indicator for FPGA resource utilization in general. So this is mainly due to 2 reasons in this case. One is that it considers the weight storage to a large amount, to 50%, but this might not actually be the limiting factor for a certain device or a certain neural network. And as you saw in the utilization results, it's not the limiting factor here. And the second issue is the problem of unstructured pruning that Yaman has already mentioned. So the unstructured pruning in general is difficult to exploit for any accelerator. And you can see here with this example of prototype B that the cost score is lower, but the resource consumption is actually higher than prototype C. And this is because it could not exploit this higher sparsity of around 40%, which naturally occurs when you go towards these very narrow bit widths of 2 in this case. So while we assume that your submissions will be a significant improvement over our prototype, there is not a linear increase in actual resource consumption to be expected here. But the nice thing is that the data flow accelerators built by Fin actually have a lot of potential to exploit pruning, either if it is structured, of course, or if the accelerator is fully unfolded. And that's why we suggest that you experiment with structured pruning techniques in the future when you try to bring your submissions to hardware. And actually the winning team, as we've heard, also experimented with unstructured pruning. So finally, let's also look at the bigger picture and see where the advantages of this style of FPGA implementation lie against more traditional implementations where GPUs are the main competition. So this graph here shows the throughput in million samples per second over the latency in microseconds, both on a log scale. And this means we want to be at the top and left here to be very competitive. And this red one here is our prototype. And this black dot here represents the current state-of-the-art FPGA accelerator from this IP DPS paper by Trickdale and others. And this also uses the VGG10 in a mixed precision variant and uses a custom flow to map this to hardware. And its accuracy is actually significantly worse than our prototype. And we also think that we can beat this competitor solution by moving past our current bottleneck. And we did some performance projections. And if we can overcome this one sample per cycle limitations, we believe that we will end up somewhere around here and beat this 500 megasamples and 8 microsecond latency solution. So for the GPU comparison, we did some measurements on the NVIDIA V100 card, which is quite large with 250 watt TDP. And we used an 8-bit implementation using the TensorRT SDK. And we got these numbers here. And we also did a projection based on those numbers for the top-of-the-line Jetson embedded GPU, which is more comparable in terms of power draw to boards like the ZC111. Now, since these networks are running in 8-bit, you can expect a higher accuracy from them, of course, but you can also see right away that even for the really big GPU, that there's a significant latency disadvantage. Now, because the data flow accelerator on our FPGA operates on a continuous stream of samples or frames, architectures like this require no assembling of frames into batches. They can just process the whole stream in one go, so to speak. While these GPUs require the frames to be assembled into batches, and this increases the latency. So for small batches like one, they cannot really exploit their parallel architecture and end up down here in terms of throughput. So the main takeaway here is that the GPUs can reach competitive throughput, as you see, but only with millisecond latency, while the FPGAs with data flow accelerators can simultaneously reach hundreds of megasamples per second and microsecond latency. And also keep in mind for all of this that this slide only shows results based on the initial VGG10 topology from 2018. So we hope to move closer to the top and to the left with more advanced topologies and techniques, such as the ones you experimented with throughout this competition. So that would be all from me, from our results. And for our final conclusion and outlook, I'll hand it over to Yaman again.
Thank you, Felix. So I'll take over the screen share here. And let me know when you can see my screen, please.
Yeah.
Okay. So, wrapping everything up, we have this interesting new frontier of deep learning expanding into all kinds of applications. In some domains, like in communications, modulation classification, we need extreme throughput and latency, which puts some very stringent constraints on what kind of neural networks we can actually have if we're ever going to meet these throughput and latency demands. Your submissions into the challenge, they really show how much smaller the models that we are deploying could actually be, while helping meet these throughput and latency targets, as well as staying over a certain accuracy. You've seen some showcases of specialized DNNs and streaming data flow in terms of what's possible with FPGAs. We can indeed get this high throughput, low latency streaming style of interface that doesn't require any patch or this kind of overhead that you perhaps don't really want as part of your radio pipeline. And we believe that the set of tools we have with Brevitas and Fin are actually well suited for exploration, because there is indeed a whole lot to explore, as the competition indicates, as well as their implementation. In terms of numbers, we have shown you some initial Fin prototypes for RF modulation classification on RadioML 2018.1 that are already achieving near 200 million baseband samples per second at less than 20 microseconds of latency, with more than 90% accuracy on the ISNR regime. And we're also happy to announce that these will be soon made available as part of the GitHub repository that's called Fin Examples, which I'll post a link to in the chat. Further work will look at, as Felix has already looked at, exploring more advanced topologies. You know, there's residual topologies, there's all kinds of other great topologies you can come up with, as our winning teams have also shown. We want to improve Fin further to improvements towards 1D and time series networks, as it was originally designed with more image classification networks in mind, but that is slowly expanding into this domain as well. And perhaps most importantly, if you've participated in this competition and if you thought this was an interesting exercise, we really would like you to be able to turn Fin on yourself and enable you to get your models running on FPGAs. We would really like you to become part of the growing Fin community, which has numerous academic research institutes all around the world, building all kinds of fantastic examples in all kinds of domains, ranging from face mask detection, speech recognition, to intrusion detection for networks. So we would love to see your RadioML FPGA accelerator as part of this bigger effort as well. With that, I would actually like to give the mic back to Michaela to wrap up, but I will say one final thing. I will ask of you, if you participate in our competition, please fill out the feedback form, whose link will also apply in the chat in a second. It will only take a minute and it will be very useful to us if you provide us with your feedback. Michaela?
Okay, so with that, let me once more thank you all the participants for their excellent contributions. We really appreciate all the effort and creativity that has gone into your submissions, and also the great presentations. I really enjoyed the lightning talk. So thanks so much for doing this. And I want to wish all the winners the best of luck. We're progressing to the global round, right? So hold up the torch and get the prize. We have all our fingers crossed for you. And finally, for the winners specifically, we'll be separately in touch via email with regards to the prize money. And I think that's it at the end. So thanks so much for attending, and be in touch if you want to work with us. We'd love to hear from you.